Okay, hello everybody. Welcome back to physics. So, today we're going to talk about waves. Just as a reminder, last week we did a bunch of circuit stuff, and last week you also started your circuit lab. You'll be working on the same lab this week, right? That's lab 10. Next week, we will do the light and color lab, and we are going to talk about light and color tomorrow. And that'll be the last lab of the semester. Yay. So that's what's going on. So today we're going to talk about waves, and let's get going. Oh, also, if you're here, if you're in the chat and you want to say hi, so I know people are here, that would be great. I always appreciate it, so I know I'm not just talking to my screen, right? Okay, so let's get started. Today we are going to talk about waves. And actually, let me give some context here. So early in the semester, we were talking about mechanics. We were talking about motion, right? You have an object and it moves, and we want to describe that motion. So we thought about things like distance and velocity and acceleration, right? So velocity is how your distance changes, and acceleration is how your velocity changes. And then we spent some time talking about why those things happen. So we looked at acceleration as being the result of forces pushing and pulling on us. We also looked at changes in motion being the result of energy. Okay. And we looked at momentum, because that was also something that could help us explain, especially when we had like collisions, right? We could use conservation of momentum to explain what happens there. So that's all kind of one set of stuff. And then since then, we've kind of been branching off into talking about kind of some cool other stuff in physics. So we talked about what happens with charge, right? Because charges are interesting, and they have these pushes and pulls, right? The Coulomb force. And then we use that to jump into talking about what happens with circuits and electricity. And that's stuff that comes up every day. Like, I have lights on right now. My computer works right now. The internet, right? Because of electricity. So that's what we've done so far in the course. What we're going to do this week is looking at waves and light, which is a wave, and understanding this kind of phenomena. So the way a wave is defined and the way it moves is different from the other kinds of objects we've talked about so far. Then what we're going to do the rest of the time, after this week, we have 3 more lectures, because next week Monday is a holiday, so we're not doing lectures next week Monday. But we're going to talk about atoms, and then we're going to talk about the nucleus, and then we're going to talk about nuclear energy. That's going to round out the semester. Okay, so today's topic is waves. And I've been having a little bit of slow internet issues today. So, let's see here. Okay. So if I drop out, I'll try to get it fixed. Fingers crossed. Okay. Okay, so we are going to talk about waves. So let's talk about waves. What observations do we have watching a group of people do the wave? So if you've been in a stadium for like a baseball game or something like that, sometimes people do the wave, where you watch it come towards you, and then you stand up, and you put your arms in the air, and then you sit back down, right? So here is, let's see if I can forward this a little bit. Here's a YouTube example of people doing the wave, and I'll make it bigger. Some of it's going to be a little bit blurry, but there's a couple spots that are really good. Okay, so what we want to be thinking about here, this is an example of a wave. We want to be thinking about what is the motion? What can we observe in terms of the behavior of the people, the behavior of the wave separate from what the people are doing. You know, how can we define what this wave is? This is not the best view, but coming up right here, there's going to be a pretty good view. So here, we see the wave, we see the people, and it passes by, etc. Okay. So that is an example of a wave. And normally I would give you guys some time to think about and write stuff down and then tell me what you're thinking about and writing down. It's obviously a little hard to do here. So I'll just give you guys some of my observations of what I see. All right. So one of the things that we see happening is that we have people stand up and then they sit down. That's like the basic motion for each person. You stand up, hands in the air, you sit down, okay? But not all of the people are standing up at the same moment, right? So if you're sitting in the stands and you're like, when do I stand up? You know when to stand up because the person next to you has stood up, right? So you stand when your neighbor stands. Right, so you can see it coming. And that's the other thing that we can see is the wave itself moves, right? You're sitting there, especially in that last bit, you could be in your seat and you see this wave of people standing and sitting, coming towards you. So that thing itself is moving, right? It's coming towards you and then it can go past you. But the wave moves sideways. So in this example, so our wave moves sideways. Even though what's interesting is the people we first saw, they go up and down, right? So that's interesting. Anything else? I think there's a couple of you guys here. I should say hi, so I know you can see me. There's a bit of a lag. I think it's worse today than usual. All right. Nobody wants to say hi? All right. That was fine. I'm going to keep moving. So this was what we observe in this specific case. And what we're going to do is extrapolate that to properties for all waves. Okay, so one thing that is true of all waves is that they move through a medium. And medium here is kind of an old use of the word. It does not mean like small, medium, large. It actually is more like the media, like the news media. Media is the plural of medium. So a medium in this sense is some kind of stuff. Something like the news is delivered to you through the media. This wave moves through the media. It's medium. Okay, so for a wave, it just means stuff. But that's the word physicists use, is the medium. So every wave has a medium. In the stadium wave, the medium was people, right? The people are the stuff who are doing the waving. They're the ones who stand up and sit down. If you have a water wave, it'd be water. Sound wave, it's moving through the air. Okay, so different materials will have different kinds of waves as well. All right, so that's true. Another thing that's true is that the molecules in the medium, the little tiny pieces of it that actually do the movement, they will move around a center point, but they don't leave it. Okay, so for example, here I am. If I'm doing this stadium wave, I'm in my chair. I stand up, so I move from the chair up, and then I sit back down. But I don't lose my chair, right? I don't move to my neighbor's chair. I don't move to a chair in front of me. I stick in my seat, even though I stood up and sit down, right? So that's usually what happens. We often, what you'll see is like if this is the little blob of material, right? It'll move both up and down and then maybe even past the point and then back up. You know, it can do something like that where it's going like really up and down. Kind of like a spring. Okay. Springs are often the medium for waves as well. Okay. All right, so that's something that's true of waves. And then the third one here is that the disturbance of the medium, what we might call the wave itself, moves at a definite speed. Okay? And how fast it goes depends on the properties of the material. Okay, so for example, maybe you have a stadium full of toddlers and they are all super keen on this doing the wave and they're all like focused for some reason. So the wave comes around and they're really spry and they're young and they bounce up and down really quickly. That wave will move quickly. But if you have a stadium full of like 80-year-olds, they might really care and they might also be focused, but it takes more time to stand up and sit down. And so then the wave itself will be slower. So depending on what's happening in the material itself, that disturbance, that thing that we see, right, that rise and fall, that change of where the material is, that thing that we call the wave itself, that can move slow or it can move quickly, but it is moving. I have a couple of examples here on the slide of two different possible kind of waves. One is like we just saw in the wave, which is called a wave pulse. So what it looks like is anywhere in the stadium where you have a seat and you're still sitting, it's flat, but then there's going to be a couple of people in a row here who are in the process of standing up or sitting down. And so this part of the standing up, sitting back, this is the pulse, okay? And this piece shifts, right? The next moment in time, maybe it's more like this, where this person finishes like standing up and this person standing, right? But these people have already sat down, right? So this pulse itself is going to move. That's not the only kind of wave. You can also have a periodic wave, and these are actually the waves that we're going to spend our time on. A periodic wave, periodic means repeats, okay, repeats regularly. So another word for like magazines is periodicals because they come out periodically, okay, so regular repeated time. And we're mostly going to deal with periodic waves because even though in a way they seem more complex, they're actually the simplest. So that's what we're going to do. All right, so here's an example of a periodic wave. Okay, there's the circle part on the left. We kind of don't care about that. It is interesting because circles and the motion of circles are related to this. This is creating like a sine or a cosine wave, and those are intimately connected, and so are waves. But for us, what I want you to look at in this GIF is just the motion of the wave itself. So what you have is this shape, and that shape is moving. Okay, so if you look at the yellow dot that goes up and down, that's like a piece of our medium, and it goes up and down, goes past the center point, right? But it never leaves it. It itself never moves sideways, but the wave moves sideways, right? So the wave has a definite speed. If you watch make it bigger. If you watch the top part of the wave, the very tippy top, that moves to the right at a definite speed. So that speed is what we would use as the wave speed. Okay, All right, so let's start digging into sort of the physics of waves, and in order to do that, we need to describe waves. All right. You'll notice before that in that GIF, like I needed a GIF, I needed a video, something that shows the motion in order to fully capture the wave. Because waves are interesting. They have things that change in space, so it depends on where you look, but also they change in time, and it depends on when you look. But we can't always just draw videos. I mean, I can't draw that at all. So what we do is we separate these two ideas out. And first, we are going to look at the space picture, where we care about position along the horizontal axis, and we ask, depending on where we look, what's happening. And then later, we'll look at time, where we ask, okay, now when are we looking? Okay. All right, so for the space picture, what you do is it's very much like just taking literally a photograph, okay? You take a picture, and so you are at a single moment in time. A photograph does not capture lots of time. It's going to be one moment in time. But it does show you what's happening across space. So this is literally just position in space, like where are you looking? Then we have our vertical axis, which we'll call y. Y is going to be a really generic variable. It could stand for lots of different things with different units, depending on what the wave is. What it will always mean is the displacement. So displacement is how far, like you have your material that is in some way waving, and we want to know how far it is from center. So usually, and for the waves we talk about, pretty much always, at least until tomorrow, this will be a literal distance, and so it would be measured in meters. But that's not always true. It's just most often, okay? But in any case, for a given wave that looks like kind of a nice sine wave, we have a couple of important places. If you go from the center line up to the tippy top here, you're finding the amplitude A. Okay, so amplitude is the farthest distance that you get from the center, assuming it's distance, but usually it is. So that's your amplitude. And then, so this wave would have a fairly big amplitude. If I drew something like this one would have a fairly small amplitude. So that's the difference between different amplitudes. Okay, another important feature is going to be if you look at the tip of this, and this is called the crest. So this down here is called a trough, and this is a crest. Okay. If you look from crest to crest, this distance here is called the wavelength, because it is the length of one wave, okay? You don't have to find it that way. As long as you are comparing similar points from one to the next, it will count. My favorite way of finding wavelength is actually, instead of looking at the peaks or the crests, I like to look at where it crosses zero. So here, I'm crossing zero, kind of going up. And then I come here, I'm crossing zero, but I'm going down. So I'm skipping that. I want to come back to the same point. Here, I'm crossing zero and kind of going up again. So these two are the same points, and this distance is also the wavelength. The reason why I like that is because that's where the numbers on the axis are. So if you're trying to read the numbers, it's actually usually easier to do it down here than to try to do it up there. The reason why your book emphasizes this is because you're less likely to pick the wrong point, because there's this middle point that crosses 0. So whichever you prefer, you can work with. Okay. But wavelength is the, this distance. If I were to draw two different waves with different wavelengths, I could have something with a short wavelength like that, and I could have something with a long wavelength more like that. So short waves are squished together and long waves are spread apart. The other arrows that are shown on this are just indicating different displacements. So again, the displacement value is just where are you along this black line. So like here I have a big negative displacement, here I have a displacement of 0, here I have a medium-sized positive displacement, and so on. It's gonna do the thing. Sorry, it's being really slow. So then I tell it to advance, and then I end up telling it to advance, like 3 times. Okay. All right, I'm gonna make this one big. And while I do so, I will redraw it on the board behind me. Okay, so here let's practice this idea. We've got a water wave. I mean, maybe not a very realistic one. I guess it would be a super choppy day on the water, but that's okay. So we have a water wave, somebody takes a picture of it. It has these big crests and troughs. We want to figure out what is the wavelength, what is the amplitude, and what is the displacement at about 2 meters from the origin. So you guys take a moment and try to find those numbers, and I will draw it on my whiteboard. Okay. If anybody wants to drop their answers in the chat, feel free to do so anytime. Right now, I'm not really seeing anybody in the chat at all. Nobody's even said hi to me. Sorry, pathetic, aren't I? Anyways, so I'm just going to keep going on. If you're watching this later, which most of you will be, whenever I do these, feel free to pause it, come up with your own answers before continuing on, right? Okay, so in this case, we're finding our 3 things. So the first thing we want to find is wavelength. Oh, I forgot to tell you the variable that we use for wavelength, which is good for you to know. Okay, so wavelength is going to be measured in meters, and it gets the variable lambda. So this is a Greek letter. Okay, pronounced lambda, it's the Greek letter equivalent of an L. Okay, so that's what we're trying to find first. We're trying to figure out what does lambda equal. What is our wavelength for this particular wave? Okay, so again, there's a couple different ways you could do this. You could go here to here and estimate like what that value is. That would be fine. I would estimate that to be around 1. And so then the difference would be 4 minus 1, and that would be a wavelength of 3 meters. Or the other way to do it, which I showed you guys before, is we can start here, and then we go to the next equivalent point, which is here, and that seems to be around 3. So once again, it would be like 3 minus 0, which is 3 meters. Okay, so either way you do it, you should get the same answer, which is nice. Now let's think about amplitude. Amplitude is going to be the biggest value here. So it looks like the number here of 0.04 was, or 0.4 was listed, but that's not all the way to the top, right? All the way up is a little bit higher than 0.4, so you'd have to estimate. But to me, it looks like it's about 0.5. And because this is water, and it's literally water that has moved up away from its normal equilibrium point, this will be measured in meters. All right, and then the next question is, what is the displacement at 2 meters? So I would write that y of 2, because y is my displacement, and then it's at 2 meters. So actually, I'll go ahead and say 2 meters. I'll put it up here. Okay. So what we want to do here is we want to come over to 2 meters, right? Because this is x, so it's measuring meters. And then I want to say, where is my thing at this point? So if we come over here, this is going to be around the negative 0.4. So that's what I'm going to say. Negative 0.4 meters as my displacement. Okay, that's our space picture. Now let's think about what happens with time, okay? I'm gonna leave these numbers up. Actually, I think I'll write them off to the side because we'll compare to them later. And I think I need a better blue marker, so I'm gonna try this one. So let's see. For our water wave, oh, that's much better. We have lambda equals 3 meters, amplitude is 0.5 meters, and y of 2 meters equals negative 0.4 meters. Okay. All right, so space is one way to think about this, but time is another. As time goes on, the appearance of the wave changes. In fact, let me go back real quick to the GIF. Here we go. So when we think about time, instead of taking a picture, we're more like we're tracing out what happened. So if we were to watch the dot at the beginning of the wave, and we see it go up and then down, up and then down, up and then down. So if we track where is its position as time goes on, we will get something that also looks like a wave, but now the axis is time instead of position. So we choose one position to look at, and then we track it. Here we go. So now my axis here is t for time. This is your clue. This is the big thing that tells you which graph are you looking at. You want to look at your horizontal axis. Is it position or is it time? Over here, we've got displacement again. So that hasn't changed. And then we've got our wave. Okay. So a few things are the same. This is still amplitude. Any other point that we look at is still displacement. But now, instead of wavelength, our equivalent is called the period. Here to here. So from one crest to the next, it's going to be the period. We call that capital T. And it's going to be measured in time, which is seconds. Okay? And again, you could also do it from down here until the next bit that's the same. That would also be the same amount of time. Whichever way you prefer doing it, get the same answers. So speaking of, here's one once it gets there. Oh, here's going to be, there we go. So many trouble with this. Okay. Here's one for you guys to try. So again, I'll give you a couple minutes and then I will go over my answer. So this is our same water wave. Now you take a video of a buoy on the water. So we're looking at one place, just this float in the water. And then we're tracking what is its displacement. Okay. All right, so let's look at this. All right, the first thing I want to find is what is the period. So again, I could start here and go there. I think what I need to do, even though, is figure out where 1 is. It's a little bit tough. I think that's why one reason I'm going to go from here to here in this case, because it looks like 1 is going to be somewhere around here. So we're kind of around maybe 1.5. Right? So I would say that the period t equals 1.5 seconds. That's how much time it takes before we repeat the wave. Okay? Because again, it's a periodic wave, so it keeps repeating itself. It takes some amount of time before that happens. That time is the period. We also need the amplitude. So once again, we come over here, we're a little bit higher than 0.4. Okay, cool. We're probably around 0.5 meters again. That seems good. And then the displacement, 2 seconds after the clock started. All right, so we come here, here's 2. Well, it kind of looks like at that point it's at another amplitude, right? At another highest thing. So my y of 2 seconds would be equal to 0.5 meters. And now we can compare these values, right? My amplitude is the same. That's good. It's the same wave, just different representations. My wavelength and my period have different values, but that's okay. They measure different things. One of them is measuring space. The other one is measuring time. And then same with my displacement. These are different because on one axis I have space, and on the other axis I have time, so they don't have to be the same, okay? All right, so an important other parameter for waves is called the frequency. Frequency gets the letter F. It's measured in hertz, which is the same as 1 per second. Okay? Frequency is something that tells you how often the wave comes by, right? So frequency is something we also have in normal non-wave life. Like if we think about something like birthdays, those are infrequent. Like you only get your birthday once a year, right? Once per time, right? Once per year. It's not very frequent. But if we think about how often you get up in the morning, well, you do that once a day, right? Once a day, like days come by much more frequently than years do. And so you could have something that happens, like maybe if you think about how often your heart beats, that's hundreds or thousands of times per day would be that frequency, whereas waking up is only once per day. So frequency is all about how often does this thing occur. So the bigger the frequency, the more often it occurs. But the more often it occurs, the smaller amount of time there is in between each thing. Okay? So frequency is going to be inversely proportional to the period. Right? If my amount of time here is huge, like a year, I get a frequency that's really small. But if my time is really small, like a second, or less than a second, then my frequency gets really big. It happens really often. Okay? So if you ever are thinking about waves, you're doing things and you get lost on what F is and what's happening there, you just want to be asking yourself, how often? Does this thing happen often, or does it happen not often or infrequently, right? Okay, so now we want to think about our water wave. We want to figure out what is its frequency. Sorry, my nose is itchy. I think it's allergies or something. Oh my goodness. So anyways, I'm sorry for always like scratching my nose. All right. All right. So in this case, we know the period, so we can pretty easily find the frequency. F will be 1 divided by 1.5, which should be 0.67. Yeah, because that's 3 halves. We flip it 2/3. Okay, good. And we can write that as hertz. It's the unit that's named after a person, but it's not very descriptive. The other way we can think about this is by calling it cycles per second. So this is telling us that every 1 Mississippi, every 1 second, for this wave, we get 2/3 of a cycle. Okay, because 0.67 is 2/3. And let's see if that's true. So, okay, here's my 1 second, right? Right here. So I start here, and I go up, and I come down. I'm at half a cycle, but I keep going until here. Yeah, that could be about 2/3, right? I'm a little bit less than 3/4, which would be at the bottom peak here, and 1 full cycle would be I come back up there. So that's another way to think about frequency, is it tells you in 1 second how many of the waves will you see. So if I had a frequency of 3 cycles per second, then between 0 and 1, I would have 3 waves squished in. If I had a frequency of half, like 0.5, then between 0 and 1, I would only have 1/2 of the wave squished in there. Okay. So that's the other way to think about frequency. All right, so here's the thing. We have looked at 2 different pictures of the same wave, right? We looked at the space picture and we looked at the time picture, and they are the same wave, but they look very different, right? The space picture has like 3 waves, 3 crests at least, and the other one has 5. How are they the same wave if they look so different? Well, a couple answers. One, of course, is that the axes are different. One of them is measuring where you look, what do you see? The other one is measuring when you look, what do you see? And so we have to think of what is our connection between space and time, right? If you cover some distance, but it takes some amount of time to do so, how do we usually think about it? We do so with velocity, right? If I run 100 meters in 20 seconds, I can figure out my velocity. And same thing for waves. Come on, there we go. All right, so here we go. We have 2 different equations for wave speed, and you can use either one. They both work. It just depends on what information you have, okay? Which one's easiest for your particular setup. So, let me kind of rewrite this stuff. Okay, we also found that the period was equal to 1.5 seconds. We saw that y of 2 seconds was equal to 0.5 meters, and we figured out that the frequency was 0.67 hertz for our water wave. Okay. So now let's look at these velocity equations. The first one says velocity is wavelength divided by period. And this one makes sense to me because we're saying one wave has a length of one wavelength. That's how far you go to do one whole wave pattern. How much time does that take? Well, it takes the period worth of time in order to make that happen. So we always divide the distance you travel and the time it takes to find the velocity, and that's what we do here. So our velocity is still going to have units of meters per second, just like always, because this is measured in meters, that's measured in seconds. The interesting thing here is I could write this as lambda times 1 over t. I'm allowed to do that, okay? When you divide by something, it's like multiplying by the reciprocal of it. So dividing by t is the same as multiplying by 1 over t. Well, we know what 1 over t is. That's the frequency. So another way to write this would be velocity equals wavelength times frequency. Here's our two different equations. And this one works too. If we think about units, because this equation is going to come up more often. Okay, I'm not going to lie. For some reason, I'm not even 100% sure what it is, but just in physics, a lot of times the frequency matters a lot more often than the time. So a lot of times with waves, these are the things that we know and care about more than that. Okay, so we'll see this equation again tomorrow. And if you ever get yourself confused, like, because it's 3 variables and you multiply 2 of them equals the other one and you forget which way it goes, you can think it through with the units. So velocity is meters per second. So the units on the other side better be meters per second, right? Well, wavelength is meters times, and the frequency is 1 over seconds. So that's fine because it's meters divided by seconds on both sides. Okay, the question is, what is the wave speed of our water wave? Don't worry about sketching the graph for the other one. We'll talk about it a little bit. But take a moment to think about what is the speed. Oh, I'll leave this not so big. There, so you can see these values. Okay. All right, so in this case, we could use either equation. We'll go ahead and use both to show you that it does work and it gives you the same thing. So in the first one, if I'm finding velocity from wavelength divided by period, in this case, my wavelength is 3 and my period is 1.5. So 3 divided by 1.5 should be 2, and that'll be meters per second. For this one, our wavelength is 3, and our frequency is 0.67, which is essentially 2/3. So those 3's will cancel. We will be left with 2 meters per second. Ta-da! It works both ways. All right, so here's another question for you guys. Again, I'm just going to show it here, and then actually I'll pretty quickly move on to the solution. So here we have the middle key of a piano, the middle C, has a specific frequency. It is at 264 hertz. So that sound wave is going to hit your ear 264 times in 1 second. The speed of sound is very large. It's 340 meters per second. So the question is, what is the wavelength of that sound wave? Okay, and again, if you're watching this later, please pause and try to work through it on your own, and then watch my solution. Okay, so here we've got 2 of our pieces of information. We know the frequency is 264 hertz. We know the velocity is 340 meters per second. And then we're trying to find the wavelength. So in this case, it makes a lot of sense to use our second equation. Velocity is wavelength times frequency. Okay. So if we plug in, we've got 340 equals unknown wavelength times 264, and we divide both sides by 264. And then this cancels, so we're left with lambda is 340 divided by 264, which I think is like 1.2 or 1.8. Let me double check. So 340 divided by 264, 1.3. It was actually 1.28, so I was kind of close. We'll call that 1.3 meters. So that's how long when you know, like longer than it's a meter stick and a third, right? Is how long that sound wave is. But there are a lot of them that hit your ear in 1 second because it travels really fast. Okay? All right. Okay, so a lot of the waves we've been talking about, and especially like the wave in the beginning, I was pointing out that the way the people moved was up and down, but the way the wave moved was side to side. And that is often, but not always the case. So there are actually 2 fundamentally different kinds of waves called longitudinal and transverse. Now let's see if I can do this for the camera. I have a Slinky that I took from the physics department before all of this began. Yay. Okay, so a transverse wave is going to be side to side. See, I knew this would be a little bit tricky because of gravity. So what I'm going to do here is I'm going to try to point this down at the desk. Here is my Slinky. This will be better. There we go. So the way I make this happen is I am pushing this way, right? So in the direction that I want the wave to move, I push my hand and then I pull out. I'm right-handed, so it's easier to do it that way, right? That is called a longitudinal wave. Transverse waves, on the other hand, now I'm going to move my hand up and down, like towards the computer and away from it. And if I do that, see how different it looks? This is more like the other waves we were talking about. So for a transverse wave, the motion is up and down of the Slinky, the side to side of the wave. So fundamentally, transverse, the motion of the kind of the bits of the material is parallel to the motion of the disturbance, right, which is the wave itself. So if the motion of the molecule is like back and forth, so this is the medium motion, the motion of the wave disturbance is parallel to that, right? But for transverse, it's perpendicular. So if the wave motion, I'll call this v instead of y. So the velocity of the wave itself is sideways, but the movement of the medium is up and down. And you can have complex combinations of these. I'll actually show you guys some examples for all of this. But those are the two basic types of waves. Okay, so again, obviously we're not doing soapbox, but take a moment and think about your answer to these. Which of these waves do you think would be longitudinal? While you do that, I'm going to prep some videos for us to see. Okay, I think that's all the ones I wanted you guys to see. Okay. Okay, so which of these are longitudinal? Well, a stadium wave is definitely not. We've seen that. If a stadium wave were longitudinal, you would shake back and forth in your seat. That's not what you do. You stand up, right? Even though the wave moves sideways. A rope waving up and down, when the rope waves because it's going up and down, but the wave moves sideways, that's transverse. A water wave, water waves are actually complicated. It could be a little bit of both, but it's not purely longitudinal. In fact, mostly it's transverse. Sound waves, now those are going to be longitudinal. We'll see the example next. Earthquakes are more complicated. We'll talk about those as well. Okay. So here's sound waves. A sound wave, like me speaking into the air, is produced by vibrations of something, like my vocal cords, and then amplified, so you can actually hear me. But fundamentally, it's the movement of air. And those air molecules, like if the wave goes this way, each air molecule moves back and forth. So this one will move, and it makes this one move, which makes the next one move, etc., until it propagates across the room or wherever. Here's an example, though, where displacement is not necessarily measured in position. So this is being measured in pressure. And pressure tells how tightly are they like pushing on each other. So when the air molecules are all packed together, they're pushing on each other really hard. That's high pressure. But when there's fewer of them, they're not pushing as hard, that's less pressure. And so what you get is, just like in the slinky, we get regions where the slinky is close together, that would be high pressure, and then regions where it's far apart, low pressure. And so that's how sound works. When we actually graph it, even though it's longitudinal, even though the motion is parallel, we still draw it to look like that sine wave, right? Because that vertical axis is not always actually literally perpendicular to the axis that the wave is moving along. Okay, so keep that in mind. something that makes this different from the water waves we looked at before. Okay. Now let's talk about earthquakes. Earthquakes are cool. All right, so let's do some of that. Press on the right thing. Okay, so earthquakes, there's a few different kinds of waves. So earthquakes are waves, in case you didn't know. Earthquakes are waves. You've got some disturbance, some oscillation at the center, and then it sends out waves through the literal rock of the earth until it hits the surface, and sometimes nothing and sometimes bad things happen, right? So there are different kinds of waves that are in the earthquake. P waves are called that because they're the primary wave. So they are body waves. They go through the literal, like through the inside of the earth primarily. They're really fast. They can move through both solid and liquid. And what's really interesting is some animals can actually like detect them. They hear them happening before humans do. So sometimes you hear stories about an earthquake where it's like, oh, my dog started freaking out and then the earthquake hit. Yeah, they heard the P wave, which I think is pretty interesting. So if we look at the P wave, see if I can make this happen. What has happened here? I feel like, sorry, this thing got, okay. Sorry, I just realized the YouTube video I had planned to show you guys got messed up because it auto-played the next thing. Okay. Anyways, here's the GIF of the P wave. So you can see here the squares here represent the Earth, and then you can see what's happening with the actual compression of the Earth, and that black square just helps you see what happens at a particular point. So this wave is longitudinal. Okay? And it's a wave pulse, not necessarily a periodic wave, although of course earthquakes can repeat. But that's the P wave. The next kind of wave that happens in an earthquake is the secondary wave, which is called an S wave. These are also body waves, so they also go through the interior of the earth. They have a slower speed, okay? So their wave velocity is smaller than the P waves, and they only move through solids. They can't move through liquids. So let's look at these guys. All right, here's the S wave. So in this case, you can see that it looks more like that wave pulse, like the S kind of shape. And the little thing goes up and down. That is a transverse wave. And what's cool about S waves and P waves is we can actually literally use them to figure out what is inside the Earth. Okay, we can, by setting up seismographs all around the world to detect different earthquakes and comparing records all around the world, we can see what's happening inside the Earth, kind of like an ultrasound, okay? Because, for example, if you have the epicenter, in this case at the top, you get P waves and S waves everywhere in kind of those top two corners. But there's a big ball of liquid in the center of the Earth, and the S waves cannot go through that. So on the other side of the Earth, that whole red arc shows where you do not detect S waves after an earthquake. But you can detect P waves kind of on the opposite side, although they never show up in those two little side bands. And that's just due to the way waves travel through different materials. But by studying this, people have been able to figure out that there is like the solid core and then the liquid and then more rock. And I think that's pretty cool. All right, next waves. So now we've got a couple other interesting waves that happen in the earthquake. These are surface waves, so they just travel along the outer edge, not through the body. But we've got love waves and Rayleigh waves. And here's where something interesting happens. So here's the love wave. Okay, so if we watch this, it's weird because it almost looks like something is happening, like that the thing is going up and down, but it's not really. They're moving to and fro. It's just that they move further along the very surface and then less far as you go deeper. That's because it's a surface wave. And it creates this weird compressed from the bottom shape. But fundamentally, this is a transverse wave, okay? Because the particle motion is perpendicular to the motion of travel. And then the other wave we can look at is the Rayleigh wave. And this one is super interesting. You really have to watch that black square. It kind of goes, woo, right? It kind of goes down and around, makes like a circle. So this is what I meant when I said some of these are combinations. This is both transverse and longitudinal because part of the motion is parallel and part of the motion is perpendicular to the axis. Okay, so that's earthquakes, which is pretty cool. But now that brings us to kind of our last topic on waves, which is what happens when waves collide. Okay, so let me show you guys a different example real quick. If you watched my collision videos that I put up during when we were talking about momentum, and hopefully you did, this will be pretty familiar. But if I have two objects, like two particles, these are solid things. These are not waves, right? This could conceivably be the medium for a wave, but they are not themselves a wave. Okay, these are particles. And so we know what happens when these things collide, right? They come in, they bounce off. Maybe they stick with the Velcro, maybe they stick with the magnets, right? But generally speaking, what does not happen is anything else, right? Like they bang into each other, right? So question is that what happens with waves? So I've got two waves that are coming towards each other. The tall, relatively skinny, and the shorter, relatively wide wave, okay? And let's look at what happens. So I have my YouTube video here. I'm going to drop into this. Okay, so what we have here, and let me make this bigger, is we're going to have the same situation. We're going to have the tall wave. Let me get this to the point where you can see it. There. We've got the tall, relatively skinny wave on the left, and then the shorter, wider wave on the right. And then we're going to see what happens when they hit each other. Whoop, whoop, and there. So interesting. They do not act like the carts. They don't bang into each other. They literally combine for a moment to make something bigger than each was. And then if we look at the video now, the tall one is this way moving that, and the shorter one is that way moving that way. They pass through each other. So instead of colliding, waves will combine and then continue as if they were never combining at all. This is super cool, okay? This is a really cool thing that waves do. Let me replay this. I mean, you guys can always replay your video, but I like to see it again too. So there they go, whoop, big, combined, and then small, and they carry on as if nothing had happened. And I just think that's so cool. Okay. So that's this video. And then what we call this is interference. Okay? They don't collide, they interfere. And interference can happen in one of two ways. They can do it constructively, where you get something bigger than originally, or it could even be destructive, where you get something smaller. So let's see how that happens. If I have my two peaks here that are combining, and they're both, positive, then the displacements will add. Okay? So as they overlap, their displacement, any part of the wave that's at the same point as another part of the other wave, they'll just add together. So these will create something bigger than what we had before, because we're literally just adding these two waves together, right? So like we've got the tall one and we've got that one, and you add those together and it creates this big goopy wave. On the other hand, if instead it looks like this, so this one's moving this way and that one's moving that way, now when they're in the same place, and you've got one that's up and the other one that's down, they still add, but one of them is now negative. And so this will cancel to become something really tiny. And what's really cool is that if you had two waves, I'm sure you guys can see that. If you had two waves that were exactly the same, but they were like this, they could completely cancel to zero. So for some moment, two waves could make zero wave. Or if you had two waves that were the same on top of each other, two waves for a moment make twice the wave. And that is how waves combine. Okay. So the really cool thing about constructive and destructive interference is you can actually use it to create what's called a standing wave. So everything we've been talking about so far have been traveling waves. The wave moves constantly. Okay? And the same thing's happening here. So in this picture, I want you to just look at one of the shorter waves. It's either blue or green. So the green wave, for example, is shorter and it's continually moving to the right. That's all it does. It doesn't do anything else but move to the right. The blue wave, which is short, is just continually moving to the left. The red wave is what you get when you add the blue and the green together. And the red wave is the one that gets really big. Okay? So at some moment, it's really tall. And if you look carefully, that's when the blue and the green wave overlap each other. So the green and blue are moving in opposite directions, and sometimes that means they perfectly overlap so that you get constructive interference. And then you get like big total wave. But sometimes the red and the green, or the blue and the green wave, are opposite of each other. So you get a peak for the green wave and a trough of the blue wave. And at that point, the red wave flattens out. So at some moment when you watch this, you get a flat line for the red wave. And if you just look at the red wave and ignore the others, you'll see that the position of the peak never changes. So if you pick one of the peaks for the red wave, it just seems to go up and down, up and down. It doesn't seem to be moving. That's why it's called a standing wave. The red wave is kind of standing in place. It's almost like the person doing the thing where it's just like just up and down, just in their own location. But that's the displacement of the wave. Like there's no sense that that peak is moving, because it's not. The peak itself stays in place. But it's being created by two traveling waves. And all that's happening is that sometimes they overlap and they add, and sometimes they overlap like this and they cancel out. Okay? So we get a moment of constructive interference and moments of destructive interference. And sometimes they kind of partially overlap and it's a little bit in between, and sure. So here's a picture from your book of that happening. The top picture on the left here shows when the two traveling waves, the colors are different here, but shows the two traveling waves are completely what's called out of phase. So they don't match at all. You've got crest lining up with trough. And when that happens, the whole thing flattens out. Okay? But then, if you wait a moment, they're moving in opposite directions and now they overlap each other perfectly. And when that happens, you're going to get maximum amplitude where the crest is, and maximum negative amplitude where the troughs are. And then you wait a little bit longer and now they're out of phase again and it flattens out. So the net effect of that is the picture on the right. So for any given instant, you would get just one of those lines. So the darkest line shows like what happens in the first top picture on the left. No, sorry, it's the one directly across from it, where you get the maximum amplitude. Okay, and then some moment later they add up not quite so tall, not quite so tall, then they're completely out of phase and it's a flat line through the middle, and then the other side starts matching up, the troughs do. And so that is how you create a standing wave. The places where there are some places where it never appears to move at all. Those are called nodes. And then the places where it moves to maximum positive and negative amplitude is the antinode. Okay, so here's where normally in class I would have you guys kind of play around with this with slinkies. Obviously, I can't have you do that because we're not in class and you don't have slinkies. So I think I'm actually going to end it here, except that the one thing I will say is one of the applications for standing waves. Let's talk about that for a little bit. Okay, so one of the major places that standing waves come up is in music, okay? If you are playing a piano, right? Earlier we saw piano example. So the way a piano works is you strike a key, and then that makes a hammer hit a taut wire, okay? And that wire will vibrate. And what happens with wires is that when you've held down both ends, you hit it and that creates a wave. That wave travels to the other side, bounces back. Now you have two waves, two identical waves moving in opposite directions. That sets up a standing wave. So you have to have two waves. They have to go in opposite directions. They have to be the same wavelength. But if they are, you create a standing wave. Now that you have a standing wave of this vibrating string, that will consistently hit the air in the same way every time, and that creates the sound that you hear. Okay? So pianos work that way. Like wood instruments work, or like you can also create it with like a trumpet or something. You've got like a pipe of air. You can also create standing waves inside pipes as well, longitudinal waves instead. Guitar is an example, so it's another string. So again, whenever you pluck the guitar string, it vibrates, and that creates a standing wave with the two waves going opposite. And as they vibrate, they then push on the air, and that becomes sound that we hear. Okay? And so if your guitar is out of tune, you just need to change you have a couple options. You can change the length of the string. That produces different notes anyways. If you want a particular note to be like the perfect frequency, the perfect note, you can change the tension. How tight is that string pulled? Because that changes the material, which changes the speed, which will change the wavelength. So that's how that all kind of works. There is so much cool stuff out there with the physics of music that we don't get a chance to talk about, unfortunately. But that's, if you're wondering why standing waves matter, that is a place where standing waves matter a whole bunch. And obviously music is a great thing that improves basically everybody's life. So we can all appreciate standing waves because of that. Okay, I'm going to call it here for tonight. Yeah, I hope you all have a good one. Bye.